Welcome to Algebra 2, Unit 8, Section 1. Today we're going to have a little review of radicals and quadratic equations because quadratics are radical, dude. Alright, so we're going to insert some video here that I did years ago, but it talks about solving radicals and simplifying them. So let's do that.
Okay, welcome to our first example problem. We're going to be looking to simplify the radical, the square root of 48. I'm going to show a long methodology of doing this, basically to show that this is how we come up with these answers when they're a little more difficult to factor out and to figure out what the simplified radical is going to be. But this should be a pretty easy one that we should have no problem doing. So first thing we're going to do is we're going to factor 48 into a product of primes. So the square root of 2 is times the square root of 24, which is the square root of 2 times the square root of 12, which is the square root of 2 times the square root of 6, which is the square root of 2 times the square root of 3. Since we are solving for squares, we're looking for pairs. And so in this case, we take the square root of 2 times the square root of 2. And the square root of 2 and the square root of 2. And those are going to match up so that we end up with 2 times 2 times the square root of 3, which is in the simplified form 4 times the square root of 3. Now, as advanced honors geometry students, we should not have any problem coming up with the perfect squares that are factors of 48. So, in doing that, we can typically look at the number 48 and find the perfect squares that are factors. So in this case, that would be the square root of 16 times the square root of 3. Now we can simplify the square root of 16 as 4 times the square root of 3. This cuts down on a lot of work if we are familiar with what our perfect squares are. The next problem we're going to be looking at is a simplification of radicals and that we're going to be adding together. So we're going to take the square root of 18 plus the square root of 32 plus the square root of 75. In doing so, the first thing we want to do is go back to our initial methodology. What's the largest perfect square that goes into 18? And that would be the square root of 9 times the square root of 2. Again, square root of 16 times the square root of 2. And the last one would be the square root of 25 times the square root of 3. Now we'll go ahead and simplify our perfect squares. So this one becomes 3 times the square root of 2 plus 4 times the square root of 2 plus 5 times the square root of 3. The thing we need to keep in mind is that radicals are treated like variables. And the numbers that are in front that are being multiplied, such as coefficients with those variables. So we would treat such as in this situation, such as square root of 2 as x and the square root of 3 is y. So we're not going to combine unlike terms. So in this case, though, we have the square root of 3 is 3 times the square root of 2, 4 times the square root of 2. This is 7 times the square root of 2 plus 5 times the square root of 3. Our like terms are combined, our answer is complete, and we are simplified. Our next example is a simplification of a radical that is a fraction under the radical sign. So we can never have a radical in the denominator. That is against the rules of math. So we don't do that. We've got to get that out of there. So we're going to show the long way, and then we'll show a little bit of a shortcut. So the first thing I'm going to do is I'm going to rewrite this as the square root of 5 over the square root of 3. Since I cannot have a radical in the denominator, I'm going to multiply this value with a value of 1 in the form of the square root of 3 over the square root of 3, therefore maintaining the same value, but eliminating the radical in the denominator. Square root of 3 times the square root of 3 is 3. Square root of 5 times the square root of 3 is the square root of 15. This is simplified. We can also write this as a fractional coefficient of the square root of 15. Now, a shortcut method that you can look at if you want to save time is basically to square your denominator and then multiply it by your numerator. And that would be a shortcut method that you can use. Please be careful when using this because you don't want to make mistakes that will come back to haunt you. All right, so now our next example, we're solving a quadratic. And there's two methods we can use. The first method is our good old SOS method of simplify, operate, simplify. So we're going to do that. We're going to subtract 9 from each side of the equation. And we end up with x squared is equal to 16. Now we're going to take the square of each side of the equation. And we would end up with x is equal to both positive and negative 4. The second methodology we could use is our factoring method, where we get all of our everything to the left side of our equation. That's the side we're usually most comfortable with our variable on, and 0 on the right. So we're going to subtract 25 from each side of this equation and end up with x squared minus 16 equals 0. This is a difference of two squares binomial. Very easy to factor. Basically, you're going to end up with x plus 4 and x minus 4. Now we set each of those factors equal to 0. And we end up with x is equal to both positive and negative 4 again. Both methodologies work well, especially if you're unfamiliar with your perfect squares and you need to do some factoring work, okay? Depending on what happens with either situation, you should not have any problem learning this method. Okay, our next problem is another quadratic. So what we're going to do now is we're going to get both or all of our terms on the left side of the equal sign so that our quadratic is equal to 0, and then we can factor it. So we're going to add 16 to each side, end up with x squared minus 10x plus 16 is equal to 0. Now we're going to use our reverse FOIL method that we acquired when we were in algebra, and we're going to come up with x minus 2 and x minus 8. Okay, just as a quick refresher, the factors of positive 16 that add up to negative 10. So we're going to now set each factor equal to 0. And in both cases, we simplify and we find out that x would be equal to 2 and 8. Both values are checkable. We can plug those in. 2 squared is 4, minus 10 times 2 is 20. 4 minus 20 is negative 16, that works out. 8 squared is 64, minus 10 times 8 is negative 80. So 64 minus 80 is negative 16, that works out. We always should check our work to make sure we're getting the correct answer. The last problem in our group of examples for section 9.1 is x squared plus 5x equals 0. And this is a problem that's a pretty basic problem. Since we've already got everything to the left side of the equation, Now what we're going to do is look for a common factor between each of the terms on the left side. In this case, we can factor an x out, so we would do is have x times the quantity x plus 5 is equal to 0. Now we set both factors equal to 0, x equals 0, x plus 5 equals 0. Therefore, x is equal to 0 and -5. Easy problems to do. Good luck.
Okay, so let's talk about this a little further now. The opposite or inverse of squaring a number is taking its square root. So the square root of 36 equals 6 because 6 squared equals 36. So we can now extend our discussion of roots to include cubed roots, fourth roots, and higher roots. So the nth root of a equals b because b to the nth power is equal to a. All right, so the parts of our radicals, right? So this entire thing here is a radical. The number a is called the radicand, n is called the index or order, and the expression the nth root of a is the radical. The radical sign is that square root sign that we are so used to seeing. Okay, so let's go through some problems here. Cube root of 27. So the question is, what times itself 3 times equals 27? And that would be 3 because 3 cubed is equal to 27. And we can do this very simply on our graphing calculator. Cube root of 216. That is 6 because 6 cubed is 216. Fourth root of 256. That's 4 because 4 to the fourth power is 256. Fifth root of 243 would be 3 because 3 to the fifth equals 243. Okay, so we have a rule here. The square root of a squared for any number a, the square root of a squared is equal to the absolute value of a. All right, that's called the principal square root. All right, so it's going to be the absolute value of whatever's under the radical sign. So for a here, the square root of 15 squared would be the absolute value of 15, which is 15. For b, we have the absolute value of -12, and that would be 12. For c, so it's the absolute value of y squared, it would just be the absolute value of y. The reason being is that we don't know whether y is positive or negative. So we would just, whatever's plugged in, if it's negative, we get the positive value. And for the absolute of the square root of -y squared, that would be equal to the absolute value of -y, which is equal to absolute value of y. All right, using a calculator to find roots, which that is out of place. We'll do that later. All right, so the nth root of a to the n. So if n is an even positive integer, then the nth root of a to the n is equal to the absolute value of a. If it's an odd integer, positive integer by the way, then n to the a to the n is equal to just a. All right, so it's you use absolute value when the root is even, and absolute value is not necessary when n is odd. So in this case, looking at this first one, the absolute, so 4 is even, so the answer would be the absolute value of -5, which is 5. In this case, it's the fifth root, so it would just be -5 because n is odd. Letter C here, this is an even root, but we have a negative sign in front of the square root, or the radical sign, excuse me. So this would be the negative absolute value of -3, which is -3. And in this case, because this is even, It'd be just negative m squared, all right, because n is even, okay? You'll see here where we have 3 and the cube root of x to the 24th. So basically you just divide the exponent by the index. You get x to the 8th. So in the second one here, the 6th root of y to the 18th, that would just be absolute value of y cubed. All right, now we'll use a calculator. So you just plug this into your graphing calculator, and these are the values you should be getting. All right, in this problem, we're going to plug in to find the resonant frequency f of a circuit. And this is the formula. F is equal to 1 over 2 pi times the square root of LC. So basically, you take your formula, and then you would plug into your calculator exactly what you see here using the fraction, right? So it would be 1 divided by 2 pi times square root of 6 times 10 to the negative 5th times 4 times 10 to the negative 9th. You get approximately 324,874. So we'd round this up because it's such a large number, and that's okay. About 325,000 cycles per second.